Good afternoon. Welcome to my lecture series on Kalman filtering basics. Today is lecture 1, the basics of Kalman filtering. What will you learn in this video? So firstly, you will learn what is a Kalman filter, why use a Kalman filter, the basic steps of Kalman filtering, and the simplest equations that define Kalman filtering. Now at the end of the video, you will not have a full understanding of Kalman filtering because it's quite a complex subject, but this series is dedicated so that you can understand Kalman filtering in better depth. Now, some quick preliminary information. A commonly used word is state, and state's used a lot in control textbooks, filter textbooks, and other parts of engineering. But at least in the domain of Kalman filtering, a state is a variable of a system that you would like to know of. So for example, if you want to know the speed of your car, the speed is a state. If you would like to know the acceleration or the position or the mass or the size of your car, again, they are all states. Again, if you would like to know the temperature of your coffee, the temperature is a state, or the volume of the liquid, or the concentration of the coffee. Again, they are variables of a system. They are all states. Now, it's important to understand what kind of state we are dealing with. Now, you can have a measured state. Now, measured states are taken directly from a sensor. So any information or signal or data that comes out of a sensor is a measured state, and measured states are inaccurate, typically have noise in them, high frequency jitters, low frequency biases and drifts, so they are not perfect. Now, you can have a true state. The true state is the exact perfect value of what's actually happening. So for example, if your car has moved 5 meters, the true state is your car has moved 5 meters. The measured state might, however, say 4.5 meters. So the true state is always a perfect, the real world value, the actual value that's occurring. Now, you cannot actually compute the true state in real life, especially in real time, because there's too many parameters, too many variables to consider, but you can get as close as possible to the true state. In Kalman filtering, we're trying to get as close to the true state as possible. Now, you can have a predicted state. Now, predicted state, at least in the domain of Kalman filtering, means that it's a state that's derived from mathematical equations. So if you handwrite or compute some calculations, the output of those calculations is essentially a predicted state. But predicted state requires a model of your system, which I'll teach you about later on in this lecture. Now, the last one is you have an estimated state. Now, the estimated state is the output of the Kalman filter. So once the Kalman filter has gone through all its steps, the output of that Kalman filter is an estimated state. Now, when we are Kalman filtering, the goal here is to get the estimated state to be as close to the true state using the measured and the predicted state. Again, don't worry about it. I'll go through it later. Okay, finally, we've understood what a state is, or hopefully understood what it is. Now, what actually is a Kalman filter? Now, a Kalman filter is a state estimator that filters sensor data using a model of the system. Now, key word here is state estimator. It's estimating the state, and then it's also using a model, which I'll explain what a model is later on. Now, the reason we need a Kalman filter is sensors are not perfect and it can experience high frequency jitter and low frequency drift. A Kalman filter can greatly reduce these type of noises, as you'll see in the next slide. Now, if you're having a control system and you have raw data entering your control system, you don't want your control system to control based on raw, noisy, and erratic data. You want smoothened, corrected data, and that's what a Kalman filter will do. It will smoothen and correct your data. Now, an extra point here is the Kalman filter is also a sensor fusion algorithm, meaning that it can fuse multiple different types of sensors together to get a better estimated state. Now, I won't explain too much on sensor fusion in this lecture series because it's a vastly more complex and it's almost like another domain of Kalman filtering. But in later lecture series, in different lecture series, I will probably go over sensor fusion. Now, by the way, you do not need to know much on Kalman filtering, if anything at all, to use this lecture series. This is designed to be the absolute basics of Kalman filtering for a first goer. Now here's a little example. This graph, I made a little Python simulation and it is GPS measured position, so you can see the spiky blue signal, that's all GPS positions over time. Now GPS is obviously X and Y, there's a latitude and longitude, but this is on a single axis. Now spiky blue signal is GPS, the red smoother signal is actually the Kalman filtered signal, and this purple thicker line is the true position. Now the purple line is the true state, and of course we can never get to it, but you can see that the red line here, the Kalman filtered line, gets very, very close to the true position. And of course you can see the noisy, erratic blue data, the GPS raw signal, is very far away from the true position, the true state. Now this is a very simple example of using GPS with high frequency jitter, and actually it's a very simple example because Kalman filtering can actually deal with this very easily. These little spikes here, Kalman filtering will happily deal with, but there's a lot more complex examples where Kalman filtering has to deal with low frequency biases, drifts, not necessarily failures in the sensor, but areas where the sensor struggles a bit, and Kalman filtering can deal with a lot of these things. This is just a very basic example. Now, why use Kalman filters to begin with? So we know that what a Kalman filter does. Now, why use it? Okay, so the main reason we like Kalman filters is because we can run them in real time. Now, oftentimes when you're estimating the state of something, you're usually in an aeroplane or inside a car or maybe the AC or a truck or something like, or a missile even, or anything like helicopter, and they need to have data in real time, but you can't give them unfiltered, raw, spiky and noisy data. It needs to control a helicopter or an airplane. You need to have smooth filtered data, and it has to be in real time. It must be in real time. Real time means that I want data right now so I can make a decision, not 20 seconds later. So for example, if you're driving a car, you don't want to know that you're going 70 miles per hour 20 seconds later. You want to know you're at 70 miles per hour right now. Again, the reason you need real time is so you can make a decision right now. And actually, this is one of the most desirable traits about Kalman filtering, is it can run in real time. Now, the next advantage of Kalman filter rather is it's robust to a variety of type of noises, which we'll discuss in later lectures, but they can deal with high frequency jitters, low frequency drifts, and a variety of stuff like that. In fact, they sometimes can even deal with sensor failures as a whole, but that's a lot more complex. Now, third reason is, like I said before, they can fuse multiple sensors together, also known as sensor fusion. You can fuse a GPS sensor and an accelerometer to get better position accuracy, but again, that's beyond the scope of this lecture series. They are very simple to implement. That's a bit questionable. It depends on the engineer, depends on the skill level, but compared to a lot of other things, they are a lot simpler to implement. And then lastly, another really good thing about Kalman filtering is it's very lightweight. Kalman filters are designed to run on they're designed to run on microcontrollers and small computers. Oftentimes aeroplanes, cars, helicopters, whatever, they use microcontrollers. They don't use a big GPU and a massive CPU. They're controlled through little microcontrollers. Satellites, they don't have a massive computer, they have to be energy efficient, and Kalman filtering can give you real-time smoothened and corrected data on a microcontroller because they are very lightweight. Now the basic steps of a Kalman filter. The Kalman filter has two fundamental steps, and every single Kalman filter, no matter how simple or no matter how complex, will always have these two fundamental steps. That is the prediction step and the estimation step. Now let's look at what they actually are. So what does prediction mean in Kalman filtering? So in Kalman filtering, remember that a Kalman filter uses a model of the system. The model explains how the system changes over time. So essentially, a model is the mathematical equations that describes your system. So why do we need a model to begin with? Well, models provide a predictable structure for the dynamics of a system. So for example, if you're blasting a rocket to go to space or something, there will be some mathematical equations that, well, they describe what the rocket speed will be over certain times. So maybe at time equals 0, the rocket speed is this. At time equals 100, the rocket speed is that, based solely on mathematical equations. So you could write it on hand and you could know the speed. And that's basically a model. A model is just a mathematical equation or a matrix that describes your system. So when you plug the values in, you basically get an output state, like maybe your speed or acceleration. Don't worry again too much on what models, how they work. They'll be described throughout the lecture series. So, little example, a model will tell you how a car speed is expected to change as you drive. So, if you have a mathematical model of the car based on how you press the pedals, so if you press the pedals in a certain way, you could almost predict what speed that car is going to go just based on those mathematical equations. Now, again, the model helps the Kalman filter predict what the next value likely is. Of course, a model can only be so precise. Now remember, as I said, that typically you run Kalman filters on cars or aeroplanes and helicopters in real time, and they only run on microcontrollers. They don't have a big graphics card or something like that. So your model can't take too many variables into account, because if you start taking more variables into account, your model becomes larger and larger, and a model with more equations and more parameters is actually more computationally expensive because it requires more calculations for the microcontroller to compute. Now, when I talk about computationally expensive, I always mean computationally expensive for a microcontroller, because we only really run, well, typically we run Kalman filters on microcontrollers. Maybe some areas they use it on bigger computers, but for a plane, it's always going to be on a microcontroller. So you don't want to have a model that's too big, because a model that's too big requires more calculations. More calculations mean it's going to be slower for a microcontroller. So you want to keep your model small, but at the same time, if you keep your model too small, then you haven't accounted for all the variables in your system, and you're not going to get as much accuracy from your model. So we figured out using a model. So fine, you've predicted the speed using some model that you found online, but what does estimation mean? So in Kalman filtering, we use a model because it provides the physical dynamics of the system, as I keep repeating a few times. However, if an unexpected event occurs in the real world, the model can't actually take this into account. For example, if you have a model that mathematically describes how the engine and the car links to the pedals, so that if I press the accelerator for this amount of time, the car will go at this speed. But yes, fine, the mathematical model is fine, but what happens if I go over ice? Or what happens if I go up a hill or down a hill, or my car races through a flood or something? Well, the model can't actually predict that. It doesn't actually know that. The model cannot tell, okay, you're going to have ice in the next few meters. It just does not know this. Again, with a rocket, if a rocket is blasted up and you have calculations and equations, you can't predict what direction wind's going to come, or even if there's any wind whatsoever. So a model can only be so good. And of course, it can't deal with unexpected events. Now, sensor measurements are noisy and vulnerable to real-world noise. However, if an unexpected event occurs, the sensors can detect this. So, for example, if you have a rocket and it's going up and the engine fails, again, your model cannot take into account the engine failure is just too complex or just not possible whatsoever. But the sensors, they can measure lots of things. They can do a lot of measurements, even though they're very noisy and half the time they don't really output a very nice result to begin with. But at least they can detect when an unexpected event happens. So they can detect whether wind happens or whether you drive over ice. That's why we need sensors. Sensors are vulnerable to noise and are very noisy, but at the same time, they can see unexpected events. But models don't tend to deal with unexpected events. Now, in the estimation stage, the Kalman filter combines both the predicted state and the measurement state from the sensors and combines them together. So that is the beauty of Kalman filtering. We take a model and we take our measurement and we combine them together. And that's what makes Kalman filtering very powerful, which we're going to see later. Now, this is a bit of a repeated slide, but the estimation state simply combines the model and the measurement to get the best of both worlds. Sensors are noisy but can detect unexpected things in the real world, as the real world is. A lot of unexpected things happen. Models give a predictable structure of how something should behave, but they cannot tell you if something unexpected happens. They are just a bunch of equations. That's all they are. And a Kalman filter estimation is the best of both worlds. It's taking the best of sensors and taking the best of predictions and models and combining them together. And that's what makes a Kalman filter very powerful. Yeah, and that's it. A Kalman filter makes a prediction, takes a measurement, and combines them together. Sorry. So, little simple, kind of a silly scenario of Kalman filtering. So, a very simple scenario. So, you left a chicken in the oven for 20 minutes and you want to get the chicken's internal temperature so that you know the chicken is cooked properly and safely. Now, you've probably cooked chickens many, many times in the past, maybe 5 times in the past. So you sort of have a good idea of what you expect the chicken's temperature to be if it's left for 20 minutes in the oven. So you predict the chicken will be 120 degrees. Now, your mum says anyway to you, your mother says, "Oh, well, I'm not happy with your predictions. You probably don't know anything anyway. Use the thermometer in my kitchen and check the real temperature." So you pull out the thermometer from the wardrobe or the kitchen, and it's not a very good thermometer, but you stick it in the chicken anyway. And the thermometer reads 105 degrees. Now, can you see the problem here? You've predicted 120 degrees. Your low quality thermometer says 105 degrees. But who will you believe more? Will you believe your own predictions or will you believe the thermometer? What happens if the thermometer reads 95 degrees instead? But remember, this thermometer is low quality, or maybe it's really old and can't do its job properly. So who are you going to believe? Are you going to believe this 120 degrees prediction that you made, or will you believe the 95 degrees on this low quality thermometer? And essentially, that's what a Kalman filter has to do. It's taking a prediction, reading the measurements, and making an estimation. Now, of course, when you make a prediction of the chicken temperature, you're not doing mathematics, you're just predicting from memory. But essentially, that is what's happening. Now, Kalman filters oftentimes have to deal with really bad sensors, and sensors degrade over time. You can't always change a sensor every year or something. Or maybe that sensor is the best it can be, and a very noisy sensor is like cutting edge as it can be, but Kalman filters have to deal with a lot of these horrible scenarios essentially. Now, I've made a little diagram here to sort of simplify what a Kalman filter looks like. Well, you have the two main blue blocks, the prediction stage and the estimation stage. And first you predict using the system model. Remember, the model is some mathematical equations. You make your prediction of what you think the system will do. You send it to the estimation stage. Now, the estimation stage takes in a new measurement and it combines it with the prediction. So the estimation stage takes a prediction and the measurement and combines them together, as we said, and then the next state becomes the current state. So the Kalman filter is always predicting the next state, and obviously as time goes on, the next state becomes the current state, and you keep going on and on and on until you turn off the device or turn off the Kalman filter. Remember that Kalman filter are running at every time step. They are not just running once and that's it. They run every single time step. You come with a new measurement, it runs every single measurement cycle. And in real time too. Now, it's also important to see this this initial prediction stage. Now, when at time equals 0, when we predict stuff, we are predicting based on previous values. But if you just started the Kalman filter at time equals 0, well, there's no prediction, there's no last state essentially. There's nothing previously measured. But instead, you have to put your own initial predictions in there. So, for example, when you start a car and when a car starts, what speed is the car? Is at 0 miles per hour. So typically your initial prediction could be something like 0, something sensible. And I'll actually make a lecture based on initial predictions and its importance. It's like a lot of the time you can get away with doing any value for initial predictions, but sometimes you have to be very careful with them. Moving on. So mathematically, how does the Kalman filter really work? So you've looked at basically all the theory behind, some basic theory behind it, but how does it work mathematically? Fundamentally, Kalman filters actually have 5 equations only. Like in its most simplest boiled down form, a Kalman filter has 5 equations. And they are split into 2 stages, a prediction and estimation. So if you already looked at prediction and estimation, the 5 equations encompasses these 2 prediction and estimation stages. So let's look at the mathematics. So equation 1, predict the next state. This is part of prediction. It says x pred equals, or x predicted equals f times x previous estimated. So that's x previous estimate, x prediction. So first we take our previous estimated state, which is the last estimate from the Kalman filter. Remember, it cycles back, and that's the x previous estimate. And we predict the current state based on the model f. So f is our model. F is it could be a bunch of mathematical equations, but it's typically a big matrix that you multiply with your previous estimate, and that's the model. The model is the matrix. So you get your prediction by taking the last estimate and multiplying it by the model. Now the output x predicted is the predicted state. Now again, like I said, when the Kalman filter starts, your previous estimation is an initial prediction you have to make, and I'll explain that later in other lecture videos. Now equation 2. This one's a little bit more complex, but let's look at it anyway. Predict the next state error covariance. Now you might be asking, well, I've already did my prediction. Why do I now need this thing called a next state error covariance? What even is an error covariance? Well, with Kalman filters, they actually run on Gaussians. They don't run on a single value. Sorry. With Kalman filters, they don't run based on a single value. So your chicken temperature, 120 degrees, it doesn't run just on 120 degrees. It runs on a Gaussian around there. So there's like a variance in there. So for example, you predict 120 degrees plus or minus 5 degrees. So that's not a single value, that's a Gaussian. And Kalman filter run off Gaussians, and we'll explain that in later lecture videos too. So we need to predict what our current error covariance P will be based on the model. P essentially, this value P over here, explains how much error you think your prediction has. That's as simple as P is. P describes the amount of error that our prediction may have. A prediction cannot be perfect. Just because you're using mathematical equations does not mean the prediction is perfect. It's also prone to its own noise and problems too. Now we have this little variable here, Q. Now Q is known as the process noise covariance, and process noise covariance actually it's a bit more complex and will be explained again in other videos, but it's about how much noise you experience in your model. So for example, if you put noisy sensor data and you made a previous estimate and now use that previous estimate, which is already noisy, and you stick it into your model, well, that model's only gonna either amplify that noise or keep that noise. And that's why process noise covariance is very important, because it's telling us about our inaccuracies in our model, and it's taking into account other types of noise. But this will be explained in a lot more further details with Python simulations later down the line. Now, obviously, just because you calculate the speed of your car doesn't mean it's correct. There will be an error, so you need this step. Again, explained later. Now, equation 3, compute the Kalman gain. This is now the estimation. So we finished the prediction stage here, and now we're on the estimation stage. Now the equation looks like this. K, which is Kalman gain, equals P divided by P plus R. P is again the same variable from here, and R is the measurement covariance matrix, or measurement covariance. So here we compute our Kalman gain K. If we expect a higher error covariance in our prediction, so if the value of P is high, that means we expect a lot of error in our prediction, then Kalman gain K will increase. Now this is almost like the adaptive function of the Kalman filter. This is the reason it can adapt really nicely, is because it's constantly computing how much error it thinks the prediction will have, and then it's basing the gain on that error. So now we have this value here called R. Now R is actually the amount of error we expect in our sensor. It's known as the measurement noise covariance. It's how much error we expect our sensors to have. Of course, sensors can be very, very noisy. For example, if you have a GPS sensor in the middle of a city, it could have hundreds of meters of error, and obviously R is going to be large because it's a larger measurement noise covariance. This is how noisy your sensor is. Again, explained in another video. And again, this equation is what lets the Kalman filter adapt over time to various amounts of noise and other unexpected events. Okay, again on estimation, combine the prediction and measurement. So here remember when I talked about combining the prediction and the measurement together, this is the equation that's used. So X estimate, X est here, is the output of the Kalman filter. So once you've done equation 4 and you've got this estimate, this is actually the output of the Kalman filter. Now you have this xpred, like x prediction, and remember x prediction from equation 1. So you have x prediction here and x prediction there. Now, again, we compute that in equation 1, and remember that we've made the prediction based on our model, but now we've also got to take z. Z is our new measurement from our sensor. So in this entire equation, we've actually just combined, we've actually combined the measurement and the prediction to get an estimate, and this estimate is designed to be as close to the true state as possible. Now, there's actually a little part and a key point here, but z minus x predicted is actually, I put it in yellow for a reason. This is known as a residual. A residual is the difference between the measurement and the estimate. Now, the measurement and the prediction, that should be prediction. So this is the residual. The residual is the measurement subtracted with the x predicted, the predicted state. And it's got a certain importance, which will be again explained in a future video. And in this step, we simply take the measurements from the sensor Z, we take our prediction from x predicted, the predicted state from equation 1, and then we use a Kalman gain to combine them to compete whether we trust the model prediction over the measurements. And that's how the Kalman filter combines the prediction and the measurement together. Again, all this will be discussed in better sense over the future videos. But essentially, K is adaptively changing, and as it changes, it trusts either the measurement more or the prediction more. And that's what the Kalman filter is doing. And yeah, this step combines the prediction with the new measurements. Now, step 5, update the state error covariance. This is the last equation. Now, we're not just done over here, we actually have a 5th step here, and we're still on the estimation. Now, we have this P equals 1 minus K multiplied by P again. So P is, remember, the state error covariance, and is how much error we expect in our prediction. Now, we finally use a Kalman gain to predict the next error covariance P. Now, the importance of this equation is over time, as you trust your predictions as you trust your predictions more and more, the error of that prediction is expected to decrease. So when you first make a prediction, you can expect large amounts of error. So P is expected to be large. But when you keep predicting, and you keep predicting, P is expected to decrease. Your confidence in your prediction increases. And because your confidence in your prediction increases, your actual error decreases. So over time, P has to change. So that's what this equation is dealing with, is changing the P. Now, if the measurements are close to what the Kalman filter expected, so the Kalman filter is making a prediction. If the prediction is very close to the measurement, the state error covariance P will get smaller. And this again lets the state error covariance change over time. And it also determines how much confidence the Kalman filter will have in the future, and again explained in the future video. So all the equations. So we have the prediction state and the estimation state. So first, we make a prediction based on the model and previous estimate. Then we think of how much confidence do we have in that prediction, and that's the state error covariance based on the model and again on the previous state error covariance, plus Q, which is some process noise, which explained later. And number 3, so we are now on estimation. 3, compute the Kalman gain. This is the adaptive function, allows the Kalman filter to adapt over time. This one and this one lets the Kalman filter adapt. And then 4, take the measurement, estimate the state. In this equation, we are combining the prediction and the measurement together to get an output estimate, as you can see in green, X estimate. And this is the output of the Kalman filter. And then 5, we simply just update the state error covariance, and whether it will go up or down is depending on what actually happened, whether you had predictable events or unpredictable events. Again, explained another time. Now, at the end of this video, don't expect to understand the Kalman filters all of a sudden. it's not an intuitive filter, let's be honest. It's not a simple moving average or complementary filter. People spend their entire lives on Kalman filters, researching how to make it better and just using it and applying it in the real world. But throughout this lecture series, I'll go through explanations, examples of Kalman filters to improve your understanding. I'll use a lot of Python simulations, some handwritten ones, some diagrams, and things you can do to aid your understanding in Kalman filtering. And hopefully by the end of the lecture series, you'll have a better understanding you'll have grasped the basics of Kalman filtering. Okay, next video. A simple thermometer example in Kalman filtering. I'll do this by hand. Thank you. I hope you enjoyed this lecture and I hope to see you next time. Please stay safe. Goodbye.